Today on NerdOut, Bitcoin DeFi. Welcome back to NerdOut, the show where we take a look at Cardano and we break it down, but we don't dumb it down. Today, we're going to do our best to break down the concept of Bitcoin DeFi. I'd like to invite up to the stage Riley, who has been working on the team. Riley, why don't you introduce yourself and a little bit about where you work and what you're working on?
Yeah. Hi, my name is Riley, and I work at Input Output Global. And the past handful of months now, I've been working on a UPLC to riscv compiler, and we accomplished that actually by implementing a riscv virtual machine, or a CEK machine, which is able to evaluate UPLC terms. And so we have serialized format that this CEK machine accepts for UPLC terms. And basically what that allows is, people can write smart contracts using Eigen or Plinth or PluTS, any of the UPLC languages that we have in Cardano for smart contracts, and then we can run them on any riscv environment.
Okay. Yeah, so let's break that down a little bit. That was very deep. So what we've been told so far about Bitcoin DeFi from a very high level, like from Charles and everybody, is that Bitcoin DeFi is just a toggle. You toggle it on, then you do your DeFi. But there's actually two components to Bitcoin DeFi. There's this bridge, and then there's also the riscv stuff that you've been working on. So can you kind of compare and contrast the difference between those two projects, maybe?
Yeah, definitely. So both of these projects that are being worked on are in collaboration with a group called Fairgate Labs, and they're also working with Rootstock Labs. So it's sort of a collaboration amongst Input Output, Fairgate, and Rootstock in order to enable Bitcoin DeFi, broadly speaking. And so bitvmx is an effort that's come out of the Rootstock Labs and Fairgate Labs collaboration, and it's what we've been leveraging thus far for a lot of the work that we're doing in terms of Bitcoin DeFi. And so there's this bridge which is being worked on by another team. I'm not working on that directly, but definitely keeping up with the chatter in Slack. And that bridge leverages bitvmx with the current design. And then in terms of the UPLC to riscv stuff that we're working on our side is also leveraging bitvmx for Bitcoin compatibility. But it is interesting because, given that we have this CEK machine in riscv, we can actually use any riscv execution environment, whether it's like Nervos CKB, which is another decentralized ecosystem, or we could target zero knowledge circuits, because there's already so much work that's been done over the past couple of years in terms of allowing for zero knowledge circuits for riscv programs and standardization around that. So we don't even have to do a lot of the work in terms of...
Right. And that's kind of how bitvmx works, right? It's using...
So bitvmx is using basically, you have this trace of computation where you're taking one step of computation and then hashing the entire trace prior to that along with the result. And so
you're just kind of rolling it up into one big proof.
Yeah, and it's not even necessarily a proof. It's like the information that you would need in order to prove that something went wrong, right? Because you're having one individual post, hey, this computation occurred, and here's this hash, which is the full trace hashed. And then this other individual says, well, actually, that's not the correct computation given the input to that program, right? There's a deviation somewhere. And so we're able to search through this trace and find the exact point where the two results are deviating. And then there's a challenge response protocol that's initiated on-chain, where there's these transactions that go back and forth to kind of pinpoint on-chain where this deviation is. And then once we have that pinned down on-chain, we're able to just prove that one step was misrepresented or miscomputed.
Right. And on the bridge side, that would be kind of how the bridge is secured, where somebody says, hey, I did this computation, in other words, move some value between chains, and then you only need one person that can say, no, actually, that's not correct, and then disprove that. So that's how the bridge is secured. But let's get back to all the acronyms you were saying. So first of all, you're doing a UPLC to bitvmx compiler. So UPLC, as we know, is the core language that Cardano uses on chain. And then we have higher level languages like Icon and PluTS, et cetera, that all compile down to UPLC. And now you're going a layer deeper, converting that UPLC into RISC-V. And RISC-V is what can run on Bitcoin. Is that correct?
Correct. Yeah. And so UPLC is very different from riscv. They're both kind of the same level of abstraction in terms of getting down to just being at a low level in terms of programming abstractions. And I think some people are more familiar with what I mean by that than others. But in terms of the differences, you have sort of one which is more like a Turing machine for those that are familiar, and it's like, we're doing things imperatively, right? We're defining what we're doing step by step, what the computer's doing, really. And it's this instruction set that does map directly to hardware with RISC-V. Right. And then with UPLC, it's a lambda calculus, so it's a lot more friendly for people that are into functional programming. A lot of functional programming uses lambda calculus under the hood, and so it's well suited to Cardano. And in terms of making it work, we could have done a direct compilation from UPLC to RISC-V, but it would have ended up being really, really complex, even more so than just implementing the CEK machine in RISC-V, because there's so many different ways to do recursion in UPLC. And so being able to actually, take all of those different ways to represent recursion and detect them. And then,
for those watching, recursion is where you have a function that calls the same function again and just kind of digs down until it finds the right result, and then sometimes digs its way out.
Yeah, exactly. Yeah. So
sometimes you got to break it down, but try not to dumb it down.
Yeah. Self-reference, right? It's I'm calling myself. I'm this thing, and maybe it's adding. And we're going to add so many times, and so instead of saying for this many times and looping through, we're saying we're going to just reduce the number of times that we have to add each time that we're calling the function. And so kind of a contrived example, but yeah, recursion is used all over the place in programming, and especially in functional programming. And so it's interesting because, again, we could have done that sort of direct compilation, but then it wouldn't have been nearly as useful for something that I think we are going to be able to accomplish. And this time when I say we, this is something that's less, IO internal and more just Casey, Lucas, and I sort of brainstorming and hey, this would be really cool. Let's, give it a shot. But I do think that obviously it's something that as the three of us, we all work together. And so definitely, if there are fruits of this labor, it'll be contributed to input output. But there may not be. I mean, we'll see. It's sort of one of those things where we're ambitional about the zero knowledge CEK. We'd like to be able to put it directly on the Cardano L1. Basically, take this work that we've done and allow for a smart contract on the Cardano L1 to then accept redeemers, which are proving that you did a certain computation for that validator, which is just written in UPLC. So you're just writing a smart contract using Icon, but then it's able to be evaluated on the L1 using zero knowledge proofs. And what's really cool about that is we can actually emulate novel built-ins. So we can go and say, maybe we want whatever built-in that you can think of and right now it's not available on the L1, but we can actually emulate it.
Maybe there's some other chain you want to integrate with. It's using a different crypto primitive. We don't have that on Cardano, let's say. You could then do that. And so then you could like support a bridge between us and insert some crazy future thing here.
Yeah. And so that's the hope. I mean, we'll see. Like I said, it's ambitional at the moment, but I definitely am optimistic about the way that could play out. And I think there's a lot of value here outside of just the bitvmx realm, right? Like I think the Bitcoin DeFi stuff is super cool. And I'm really excited about enabling further programmability on the Bitcoin L1. I'm almost more excited though, in terms of Bitcoin DeFi. I'm more excited about just the bridges than I am about like native programmability, because even if you did have native programmability on Bitcoin to the point where it was expressive enough to do some of these really cool like lending protocols, for example, it would be pretty expensive to do that on the L1. It wouldn't be very efficient, and a lot of Bitcoiners would cry and call it spam and you know, raise pitchforks and stuff. I think that if we have just bridges to what could be considered other L1s or side chains or drive chains, any of these, you know, different types of things that you could have bridges to, I think that is more compelling in a way. And I'm really excited about sort of the vision that we discussed at the Bitcoin DeFi talk in Vegas with the toggle, right? I think that the vision for the user experience around it is very compelling. And what we're doing,
because to date there are Bitcoin, you know, side chains, partner chains, but most of them are secured with just a signature or a multi-signature. And so there's somebody that's controlling that bridge. And this is different in that it's actually quite a bit more decentralized. Can you talk about maybe some of the, I know you're not on that team, but can you talk about, you know, the one of N type of proving situation, or how that bridge works?
Yeah. So in the original BitVM white paper, which was proposed by Rob and Linus a couple of years ago, I'd have to go look up the exact date, but in any case, that paper came out a couple of years ago, and you know, it uses the upgrades from Taproot to allow for programmability, and it was a two-party system. So you know, you and I could do a system where we're able to, between the two of us, dispute computation on chain, and that works great. It wasn't very efficient, and it requires, in order to use it, non-standard Bitcoin transactions. And what that means is, like, you know, they're valid according to the ledger, right? They're able to be in a block, but nodes will not accept them into their mempool. And so you try and submit this transaction, and it's not going to propagate through the network, right? It's valid to put in a block, but in order to actually get it into a block, you're probably going to have to work directly with a miner or be a miner yourself. And so right now, what we're seeing is there are a couple of companies that are actually bribing miners to include these transactions that are non-standard, that won't go into regular mempools, but are valid in blocks. And so they're doing that for bridging, and they're using BitVM as opposed to, you know, something like bitvmx with the there's some optimizations you can use for bitvmx to allow for standard Bitcoin transactions to be used, and you know, unfortunately some companies are petitioning to use like this non-optimized technology to accomplish the same thing, and I'm kind of hoping that they don't win that argument, because we can just optimize and we don't need to bloat the chain needlessly, right? But yeah, BitVM was, you know, getting back on track, BitVM was just a two-party system, and it's sort of allowing disputes between you and I, whereas then bitvmx is a, you know, one of N dispute system. So like you said, you know, there's N people participating, say 50, 100, maybe it's only 10.
But only one has to say, no, that's not valid, to kill it.
Yep. And so that's a much better security model than, like you pointed out, a multi-sig where it's just say like 5 out of 7 keys are required, because we've seen even in situations where teams are completely honest and do their best to maintain good security, they can end up accidentally having 5 people who fall victim to a phishing scam or something else that causes them to sign a transaction which they wouldn't otherwise sign. And so I'm very much of the belief that we should use programmability to allow some of these use cases and not just multi-sigs. But I also don't think we need to be sort of pushing this whole non-standard transaction thing, right? It just doesn't make sense. Especially, I don't know if you heard, but bitvm3, the white paper for that came out just the other day, and they have a bunch of optimizations that they've made. I still don't fully understand it at all. I'm trying to understand. I'm not like a cryptographer, right? I'm an engineer, but I'd like to, learn more about cryptography. I understand some of it. They're using something called garbled circuits, which I had, I only had heard of like once prior to reading this paper, and the bitvm3 paper is only 3 pages long. It's like a very short, brief paper, but they mention like some of these terms where you're like, what is that even referring to? And so I'm reading through this quote unquote gentle introduction to garbled circuits from MIT, but they've been around, according to what I saw yesterday or the day before. They've been around since like the 80s, so it's not like new cryptography, but it is.
Yeah, I mean, a lot of this, even zero knowledge stuff has been around for a very long time. It's only recently become useful. So
yeah, it's been more optimized recently and more attention's paid to it. People are like, oh, we can actually do something with this other than just have it, do verifiable computation in the cloud, which is cool in and of itself. But like, I think the blockchain use cases make way more sense.
Yeah, absolutely. So what's next for you? Like, what are you, where are you going to go next? What are you working on now?
Yeah. So at the presentation or at the, at the lunch and learn, and during my segment of that, I talked about how we implemented the CEK machine in RISC-V basically by hand. We recently decided that during early stages of implementing some of these built-ins, we decided that it makes more sense to do a lot of these built-ins in a slightly higher level language than RISC-V, and then compile them to RISC-V and have them available that way, just so that we can get all of these built-ins in a timely manner and have some of the cryptographic primitives enabled as well in a timely manner. And the optimizations that the compiler does for C and for Zig is already pretty highly efficient, and in some cases going to be better than what we could write by hand anyway, just because the compiler is taking into consideration some things that maybe we won't. And so we're actually rewriting, and I stayed up most of last night doing my best to contribute some of my piece, because I've only worked on some unfinished CEKs so far, and I contributed a bunch of Zig code last night to the in-progress CEK that we're doing. We're rewriting the CEK in Zig just to allow for, like I said, us to create some of these built-ins really efficiently and have them all available, hopefully. I mean,
so what built-ins are you looking at playing around with first?
Well, obviously the built-ins for integers and byte strings are important as like a first thing, and that's where we started with the implementation by hand. We had a couple of built-ins already available and ready to go and working and tested, but we're going to be going back to having those hopefully, later this week, next week. We'll be getting back into having all the integer and byte string built-ins available, and then from there, lists, maps, all of these different things that are available in UPLC as data types we want to enable. And then we also definitely want to enable cryptographic primitives, not just the BLS ones. So like,
right.
you want to enable basically everything that's available in Cardano. And we weren't sure if that was feasible when we were doing it by hand, but now it's like pretty obviously feasible. And then additionally, we want to have the built-ins that maybe are useful for, just interesting stuff available on top of that. And so we're looking to have multiple like compilation modes. So if you're targeting bitvmx, we'll have one set of built-ins available, maybe in, if you're targeting Nervo CKB, we'll have a different set. If you're targeting this ZK CK that we want to do on the L1, we'll have a different set. And so there will be some interesting stuff we can do around that. And a lot of the experience there in terms of having these different modes and stuff, and having like a nice CLI tool, some of that was Lucas who suggested it. And it's funny because Lucas is primarily working on midnight related stuff, but he just last week kind of was like, hey, this sounds really interesting, and since people keep thinking that I'm involved with it anyway, I'm just gonna insert myself in here and get involved with it a little bit. And so he's helping us out, obviously not full-time, but part-time. He's helping out, and it's nice to have him working on it with us.
So. Working on some developer experience, nice to have stuff. That's kind of what he's doing on Midnight. So
exactly.
I've been working through Midnight myself as well recently. So the developer experience could use just a little work, but it's getting there.
Definitely moving in the right direction from what I've heard. I haven't had enough time to play around with Midnight yet, but I'd like to get some more experience hands-on.
It's a little mind-bending at first for me, but I'm slowly learning it. In any case, so for the viewers at home, basically what we're talking about is Aiken itself kind of being able to upgrade its own language beyond the standard Plutus upgrades. Is that kind of what we're talking about? So we don't need hard forks to build big new chunks of functionality, really.
And not just Aiken, but again, like this is a UPLC.
Anything that targets UPLC, right?
Exactly. So whether it's, there's a Scala language called Scalus, there's the PluTS, there's Imperator Lang, there's Plinth, obviously, which is sort of the canonical, like original language. There's Plutarch. Plutarch is basically writing UPLC by hand. I mean, it's like that low a level. So I only know like a handful of people who actually use Plutarch, because it's great for writing optimized code, but it's just like not very friendly for people who are writing
one step above assembly, maybe.
Yeah, exactly. And so all of those languages are going to be able to benefit from this, not only in terms of the bitvmx stuff, but then also if we're able to get this zero knowledge CEK working on the L1, that would be super cool, and it would allow for new built-ins. There's going to be some limitations around that, right? Like we're still only able to get the same information from the transaction. It's not like we were able to do new transaction formats or anything, but
but if you wanted to do new crypto or new functionality,
I think crypto is probably the most compelling use case for it, right?
Yeah, just so you can do more bridges and validate wallets that are signing from other chains to do a transaction on Cardano. I think that's interesting.
You might also have computation that's like super expensive to do, and so you don't want to have it done on chain, and you're able to do it off chain with this, right?
You do it off chain, you verify the proof on chain, which is a whole lot cheaper than doing the whole thing. Yeah. So, no, very cool. Well, Riley, I want to thank you for stopping by, and stick around after we close out the video. I'll chat with you a little bit after that. But thank you for sharing what you're working on and what's coming with Bitcoin DeFi. And with that, nerd out.